For my term project, I decided to research the physics of hockey. To start, we'll separate the game into two parts, skating and shooting. Then we'll analyze how both of those aspects of the game relate to the subject of physics. What most people don't know is that a hockey blade actually has two edges with a hollow in the middle rather than one singular blade. The radius of the hollow determines how sharp or how deep your blade will cut into the ice. In hockey, when turning in a circle at high speed, you can feel a centrifugal force pushing you outward. You counteract this by crossing over and applying a centripetal force with each push. In order to find centripetal force, we need to first know my velocity, which we can find using this equation. Next, we'll be doing an experiment to see how much work and power I am applying when accelerating up to top speed. I skated from the blue line to the red line, which is 7.62 meters. I weigh roughly 75 kilograms with equipment. Using this equation, we can find work. I apply 5,600 joules to travel from the blue line to red line. Now we're going to do 3 time trials to determine how much power I'm applying to travel. Using my average time of 1.8 seconds and the equation for power, we can determine that I generated 3,111 watts of power skating from the blue line to red line. If you have ever wondered why ice hockey or speed skaters push to the side, or, for example, if you have been ice skating, tried to skate and realized you're not going anywhere, that's because ice skate friction is asymmetrical, which means they glide going forward and grip on the sides. So in order to propel yourself forward, skaters have to push off the side of the blade. Now we'll move on to shooting. First, we need to understand how a hockey stick works. Every stick has a label indicating flex, which is how much weight it takes to reflect a stick 1 inch. Most senior sticks range between 77 and 115 flex. However, there are always exceptions. Zdeno Chara, a 6'8" defenseman, has a 65-inch stick, the longest stick allowed in the NHL, with a flex rating of 130. He broke the world record in 2012 with a 108.8 mile/hour slap shot, 48.64 meters per second in the name of physics. In hockey, there are 3 main types of shots you can take: a wrist shot, a snapshot, and a slap shot, with a slap shot being the hardest of the 3 and a wrist shot being the slowest. This slow motion footage from the YouTube channel Smarter Every Day shows clearly how the player uses the ice about 6 inches to a foot behind the puck to generate and store potential elastic energy in the stick and accelerating the puck faster than he could swing the stick himself. And also notice how the blade of the stick outruns the puck after it is released from the blade. Shots are also impacted because of inertia, or a matter's tendency to remain unchanged unless acted upon by an unbalanced force, which in this case would be the stick accelerating the puck, creating greater flex in the stick and a higher final velocity. Newton's third law is not forgotten. Every action has an equal and opposite reaction. Every stride burns your energy, cuts the ice and dulls the blades. Every hit with an unbalanced force will send the lesser man onto the ice. Every shot wears down the fibers of your stick and the tape of the blade, and every block shot is a surprise for tomorrow. These are just some of the physics involved in ice hockey. If there's anything you should take from this, is never keep your head down, because physics hits hard.
Too young to die.